My dear friends, welcome to Rajshekhar classes on Applied Data Science with Python. This is lecture number 404. In this lecture, we will try to understand regression using decision trees. We have seen decision trees for classification till now, and how did we do it? Suppose this is my decision tree. Let me assume this is my decision tree at leaf node. Leaf node means let me assume this leaf node. At leaf node, I have n1 positive points and n2 negative points. This is n2 is negative points. If n1 is greater than n2, given a query point xq, what is my xq? Given a query point xq, using these condition here, using these condition, if the query point arrives here, let me assume my query point xq arrives here, isn't it? I will declare it as my class label. What is my class label? Yq is positive, isn't it? Because we have more positive points than negative points. This is how my decision tree actually works for classification, isn't it? For regression also, decision trees are very easily extended and works very well. Decision tree works very well for regression. That we must understand. Decision tree works very well for regression. So the way it works is, so you don't use information gain. You need not use information gain anymore. Information gain is used for classification. There are similar ideas called mean squared error. What is that? Mean squared error. Mean squared error, that is, I can say MSE. Mean squared error or median absolute deviation, or median absolute deviation. Median absolute deviation or median absolute deviation or median absolute error. Median absolute error, isn't it? There are similar ideas called mean square error, MSE, or median absolute deviation or median absolute error. So we use mean squared error or median absolute deviation or median absolute error. We use these for regression, and the way we use as follows. All these are useful for what? They are useful for regression, isn't it? In the case of classification, what we used information gain, isn't it? Yes. Suppose I have a, let me assume like this. Yes, suppose I have a data set D. Let me assume this is my data set D. I have a data set D here. For each of the points now, my yi belongs to R, isn't it? In regression, yi belongs to R. At root stage, I will take the average value of all the yi's here. Yes, mean of yi, isn't it? That is yi cap. That is average values of all yi's here, average, which is equal to mean, or even sometimes I can take median also. Mean or median. For every point here, I will predict yi. Yi is mean of yi's or yi or median, isn't it? So now every point here, my yi cap, mean of all the values of yi in your D, it could be either mean or median. Of course, median has more tolerance. Median, I can say median has more tolerance. More tolerance of outliers. This we already discussed long back, isn't it? Suppose I am trying to break it using some feature. let me assume I'm going to break this one by using some feature. If I am trying to break it, let's assume I will get a data set D1. Let me say I'm breaking this capital D by using some feature. Let me say let's assume I will get data set D1. Let me say this is my data set D1 and data set D2. This one is data set D2. So in my data set D1, my yi cap, this is yi cap, here is basically mean or median of yi's, isn't it? In data set D1, what is my yi cap? It's a mean or median of yi's in data set D1. Here my yi's in D2, what is my yi cap? Median of yi in D2, isn't it? On data set D2, we have two data sets D1 and D2. Instead of using information gain, I will use something called MSE. MSE means mean squared error. What is mean squared error? At this stage it's nothing but, what is mean squared error? Mean squared error is at this stage yi minus yi cap whole square summation sigma equal to 1 to n, 1 by n, isn't it? This what is this? This is the square of the error. Yi minus yi cap whole square means square of the error, and 1 by n means if this is your this entire thing is mean squared error at this stage, isn't it? At this stage I have two data sets. How many data sets I have? I have data set D1 and I have data set MSC. I have two data sets compute the MSC for data set D1. I have to compute MSC for data set D1, and I will compute MSC for data set D2, and I will take weighted sum of it. Weight 1. Let me say there is two weights. There is weight 1 and weight 2, isn't it? Weight 1 and weight 2, sum of it, just like the way we did weighted sum of entropies. So here I have weighted sum of mean squared errors at this stage. How can I calculate mean squared error at this stage? Just see this one, W1, that is weight 1 into mean squared error at data set D1, then W2 weight plus W2 MSC at D2, isn't it? I am multiplying MSC at D1, I am multiplying MSC with MSC mean squared error at D1 with weight 1, and MSC W2 with MSC mean squared error at I can say at D2, isn't it? That is weighted summation, isn't it? Because I have two data sets. Now whichever feature reduces the error, isn't it? Because 1 by n summation I equal to 1 to n yi minus y cap whole square is error at the stage. It's error, isn't it? Basically it is the error at the stage of D, data set D, isn't it? Error at this particular stage. This is error at this stage, just like an entropy in classification. Here we have weighted entropy at this level. I have weighted entropy. So if I have, let's say, two features, let me say I have two features F1 and F2. Let me assume I have two features F1 and F2. Is if I have, let's say, two features that I have to choose between, I will use both features to split. I will use feature 1 to split this particular data set. Even I will make use feature 2 for splitting this particular data set, isn't it? To split them. Whichever feature reduces in feature 1 and feature 2, whichever feature reduces the error or the mean squared error, I will pick that feature. Whichever feature reduces the entropy, I will pick that feature in classification. What I was doing, I was picking the feature Fi that was reducing the entropy, because the ideal entropy, the best entropy for classification is 0. That one must understand. What is the best entropy for classification? The best entropy for classification is 0. This is in the classification. Similarly, in the case of regression, I pick feature I that reduces my mean squared error, because the best mean squared error is 0, just like best entropy being 0. Isn't it? Instead of mean squared error, what is the mean squared error? A mean squared error, given a bunch of points, what you have to calculate? You have to calculate sigma 1 by n into sigma I equal to 1 to n yi minus y dash whole square. That is mean squared error. This is your mean squared error of y given data set D, isn't it? This is mean squared error of y given data set D. Similarly, mean absolute error or mean absolute error, I can say mean absolute deviation, isn't it? How can I calculate mean absolute? It's very similar, isn't it? Take this take the median of absolute errors. How will you calculate median of mod of yi minus yi cap? This is same as mean absolute deviation, isn't it? That we saw in exploratory data analysis. We can use which one you can use? Either you can use mean squared error, or you can make use this one, median of yi minus y cap, isn't it? You can make use any, both of them are possible. So at the end of the day, what is the lowest mad value, isn't it? Median absolute mad value. This is also 0. When you break a data set capital D into two parts using any feature, we are trying to reduce our error. In the regression, it is called error, and in the classification, we are trying to reduce entropy. So the good part is decision trees do very good job of even for regression problems. Just let's take an example. This is very nice scikit-learn. You can check this on scikit-learn org stable modules tree.html, isn't it? What it says, what is my x here? What is my x? Just check this one. This is my data. All these I can say, just see, this is my x. I'm taking x here, and what this one is y. Let me say y belongs to R. My original data is like this. This is my function. What is my function? This is my function, isn't it? If you want, you can go back and you can check, isn't it? We are trying to find y equal to f of x. The regression, y is real valued, y belongs to R, isn't it? This is a problem of regression, of course. I have noisy points like this. What are the noisy points? These points are noisy points, isn't it? These points are noisy points. I have noisy points. My actual function is like this. This is my actual function, isn't it? This is my actual function is like this. Look at this. If my depth is 2, just see, maximum depth is 2. What's happening for depth equal to? If you observe carefully this diagram, we have maximum depth equal to and maximum depth equal to 5. If depth equal to 2, what is a regressor? Anyway, let me go back and show you. Yes, this must be the case, isn't it? This is my, just let me repeat. These are outliers. 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 This is actual function. This one is actual function, isn't it? Now let me consider my maximum depth equal to 2. Maximum depth means what you are getting here. You are getting like this. 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 Let me show it again. Yes, maximum depth equal to 2. This is x. This is what is this? Just see, maximum depth equal to 2. What's happening for maximum depth equal to? This is maximum depth equal to, you are getting this. You are getting this, isn't it? You are getting this, isn't it? Yes, you are getting this. You are getting this. And you are getting this, isn't it? Means what? Here I get this plot. The original function is this, what is this original function? This one is your original function, isn't it? This is the original function. This is because my depth is of only 2. What is my maximum depth? This color, maximum depth is only, just like in the case of classification, lower depth means underfit. In the case of classification, lower depth means, what is the meaning of lower depth? It is underfit, isn't it? What is if higher depth means? Higher depth means what? Overfit. Overfit, isn't it? If I make depth equal to 5, what happens? What happens if I make depth equal to 5, maximum depth equal to 5? I will light and green line. Just see what is this? Maximum depth equal to 5 means I will get this one, isn't it? How am I getting maximum depth equal to 5 means which is overfitting to the noisy point. All these are noisy points. Is it not overfitting to the noisy points? If I they just see this is, it's overfitting to the noisy points. It is overfitting to the noisy points. Just see, this one is overfitting to the noisy point. Just see, these are the noisy points. These points are noisy points, isn't it? If you keep depth equal to 2, if you keep depth equal to 2, too small, isn't it? You are going to underfit. For depth equal to, it's underfitting. If you keep depth equal to 5, it's overfit, isn't it? But the true line, what is my true line? This is my true line. But the true line is this one, isn't it? But the true line is a red line, isn't it? The true function y equal to f of x. This is my true function y equal to f of x. So one good thing, when you do regression using decision trees, what you get are lines. Look at these green lines and blue lines. Just see, you are getting green lines and blue lines. You are getting lines. You are getting lines, isn't it? You are getting lines. Just see, you are getting what you are getting. You are getting lines, isn't it? Yes, you are getting. Look at these green lines and blue lines. They are axis parallel. Just see, these lines are axis parallel, isn't it? These are parallel. And another, what are the other lines? If your depth equal to 5, these are the lines, isn't it? Just see, if your depth equal to 5, you are getting lines. Again, you are getting axis parallel lines. So even decision tree regression tries to find a curve. It is never just like smooth curve. It is never like smooth curve. See, you are not getting just like smooth curve. You get a very smooth curve. Decision trees will not work perfectly well. There are variations of decision trees called random forest and boosted decision trees, which can get sort of smooth region wise. You can get smooth region wise. Yes, let me repeat. There are variations of decision trees called random forest and boosted decision tree, which can get sort of smooth region wise, smooth, but you will never get a neat curve like this. You will never get a neat curve like this, because it's trying to approximate what decision tree it's trying to approximate this smooth curve, but here you are getting axis parallel line. Just like in classification there are hyperplanes and axis parallel, in regression trying to fit the curve, all the planes or lines that you will get also axis parallel, just like classification. Just go through this lecture. If you have any difficulty, just please keep a comment. Just see, these are the axis parallel lines, isn't it? Yes, just go through this. Just see here, same thing. Maybe I think it just see, here you have for what is for maximum depth equal to. What about for maximum depth equal to 5? Just see, maximum depth, it's overfitting. Is it not overfitting? It's overfitting, isn't it? Overfitting for noisy points. Just go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.